We will now start a series of presentations on the topic of security, and we're going to kick off with Simon, who's going to talk about some working that he and a group of people have been doing on securing APIs in an NMOS environment. Simon.
So thanks, Brad, for the introduction. I work for BBC Research and Development, and specifically I work within the team that researches IP broadcast, and we've been involved for a long time with AMWA and the NMOS APIs. But it's not specifically the individual APIs that I'd like to talk to you about today, but instead, looking across the whole APIs, I want to talk about how the AMWA NMOS API security group has been working on how we're going to put some security around those APIs. So that group includes a group of different companies, ourselves at the BBC, Riedel, Fox, and a few others, and we've been collaborating together to work out how we're going to do some security with NMOS. So why do we want to do this? So we could just take the NMOS APIs and run them on a completely isolated network, right, without any access to the internet, and you could argue maybe that's enough. But if we're going to get the maximum that we possibly can out of the NMOS APIs, if we're really going to realize their potential, we need to be able to run them in other environments. We need to be able to run them on the cloud, or we need to run them on networks where we don't fully control the security. But even then, even running them on an isolated network, that may not be sufficient to ensure the security of the APIs. For example, you're still susceptible to social engineering attacks or attacks involving putting software on removable media, for example. So we need to think very carefully about how we secure these APIs, because we know that the broadcast industry is a target. We saw a few years ago the attacks on TV5 Monday. They were attacked from outside and had all their channels taken off air. So as broadcasters, people don't always agree with the things we're saying, and that can make us extremely serious targets for people who wish to do us harm. There's kind of an added benefit that we get as well from applying securities to these APIs, that as well as protecting against deliberate abuse of the APIs, we can also protect against accidental misuse of them as well. So part of the reason that the NMOS APIs are the way they are, and that's to say that they're HTTP APIs, the same as used by Google, by Facebook, by all these large companies, was that we knew that when the time came to start looking at how we could secure these APIs, the technologies were already out there. These are used out on the open internet for serving millions of people, and therefore we knew that we could then apply these same technologies to the NMOS APIs and secure them in the same way. And from that point of view, the NMOS APIs have always been securable. There's nothing stopping someone taking the kind of techniques and technologies that I'm talking about today and putting them in front of an existing NMOS implementation. So the work of the NMOS API security group has very much been around kind of two different things. One of which was working out how we're going to take these IT industry standard best practices and apply them in the NMOS APIs in the best way to make sure that we're getting the best possible security. And also around ensuring that we maintain the interoperability that's so important to the NMOS APIs. We've worked really hard to make sure the NMOS APIs are going to be interoperable between different vendors, and now we're coming to make sure we can secure them. We need to make sure that we don't break that interoperability, and we do this in an interoperable way. So what do I mean specifically when I talk about security? Because that's quite a general and vague term. So I'd like to kind of define 5 different areas that we talk about when we're talking about API security. So the first of those is confidentiality. And that's ensuring that as traffic is passing between the API client and the API server, that if it's intercepted, it can't be read. And the reason we want to do that, if we take ISO4 as an example, if someone were to intercept information being passed from an ISO4 client to the server, that contains a lot of information, as we saw in Anna's presentation before, about the device itself. It involves MAC addresses and IP addresses. And that tells an attacker an awful lot of information about that broadcast network, and we don't necessarily want to hand that over to them. So we need to make sure we have this confidentiality. Identification. So we want a client to know that the server it's talking to is the one that it thinks it is. And that's important for similar reasons to confidentiality. It's all very well us protecting our traffic as it's moving over the network, but if we're sending it to a server that's owned by a malicious party, then we may as well not bother. If we're being duped into sending our data somewhere it's not meant to be going, the confidentiality won't help. So integrity, so this is perhaps slightly different. This is our ability to know if the traffic has been tampered with as it moves between the client and the server and then back again. So here maybe let's take an example of the ISO5 connection management. If someone is able to take an ISO5 routing request and change the IP addresses in it or change the SDP file in it, then they can potentially change the way that we're routing our signals around our broadcast center. And instead of us rooting out the program we'd intended, maybe an attacker could root out a playout server that they'd put some propaganda material on maybe to air instead. And that's a very alarming scenario. So we need that integrity. Authentication, the client can check packets actually came from the API it is interacting with and vice versa. So again, this is about knowing that the traffic you're receiving is actually coming from where you thought it was and you're not being fed, for example, false registry information from ISO4. So the final area, and perhaps slightly different from the others, is authorization. And that's about an API such as ISO4 or 5, knowing that the client that is interacting with it actually has permission to undertake the activities that it's trying to do. So take as an example here, again, ISO 5 connection management. You might have a multi-studio facility, and you might have a director in Studio 1 who needs to be able to control the connection management between his cameras and his multi-viewers and all his other broadcast devices. And you have a second studio which is running a completely different production. You don't want that director in Studio 1 to be able to control all the devices in Studio 2. You want to be able to restrict them from doing that. And authorization is how we do that. If you're not authorized to make those changes, then you can't do it. Okay. So the way the technology of security works kind of naturally divided up the work areas of the API security group into 3 distinct blocks. So the first of those was connection security. So that's kind of our integrity of data, our confidentiality of data. And then enabling trust, as we call it, which is about knowing that the server you're talking to is the one you think it is, that data is coming from that server. And then the final one is client authorization, this business, as I mentioned just now, of stopping people doing things that they're not meant to be doing on APIs. And Riedel and Arne have been doing quite a lot of work in this area, so Arne's going to be doing a presentation straight after me about the authorization side. So I'm going to cover off these 2 areas at the top. So you can think about the authorization side as being a kind of application level. It's pretty aware of like how a TV studio works, I suppose, in that it's talking about the actual management of credentials and permissions. I'm going to talk a bit more about kind of a transport layer, if you like, so how the data moves around our facility, but it's a bit more agnostic to what domain it's in. This is all kind of stuff that you could use for pretty much anything. But it's important maybe to say what we're not talking about today, because there are other security areas that you need to think about. There's kind of a network layer to this as well, so that's around, can I just walk up to your switches and plug any old thing in, or is there something stopping me doing that? Is there something isolating my network from the internet, be that a firewall or a proxy or just simply an air gap? So there's kind of a whole level of security there that I'm not going to talk about. And also physical security. Can just someone wander into my apps room and start pulling out cables? Is my organization susceptible to social engineering attacks? These are things we have to consider too, but they're outside the scope of API security that we're going to be talking about. Okay. So, first of all, this connection security then, this ensuring that data can get backwards and forwards without interception or corruption. So, for this, TLS is the protocol that we're going to be using, and that's almost ubiquitous across the internet. You probably use it every day when you do your online shopping, your internet banking, and a few months ago the BBC News website actually moved to using this as well, so you use it when you're getting your daily updates, okay? So it's the way that we do security on the internet, and it's used globally by some of the biggest names on the internet. So TLS it kind of tunnels the raw HTTP traffic that we use in the NMOS APIs through itself, and it encrypts it, and it ensures that we have trust between the client and server. And in order to be able to do that, it uses a range of different algorithms, okay? There are lots of different parts to TLS, and each of those parts, each of those algorithms, we have lots of different choices about the ones we select as well. In the current version of TLS, there are hundreds of different combinations of algorithms. And it turns out this is one of the problems around using TLS, in that we can make insecure choices of these algorithms and actually end up using TLS in a way that's not secure and in a way that's not necessarily compatible. So an important piece of work for the API security group was to choose different combinations of these algorithms that work together that we know are secure. So just to give you an idea of how these are used, when a client contacts a server, it'll do this kind of handshake. And at the top of the handshake, it does a client hello, and it says, hey, I'm a client, I want to use TLS, and I can support these ciphers, these algorithms. They're called a Cipher Suite when they're used together. And I support this version of TLS. The server will select the Cipher Suite it wants to use, and it will return to the client with its choice of TLS version and Cipher Suite, and also a certificate that belongs to the server. You may have heard about these certificates that servers have to hold, and they contain, among other things, the URL that the server is hosted at, the public key of the server, and also a signature that can be used to check the integrity of that server. Okay? The server also returns a random number, and that random number is used by the client to generate a secret. And that's quite important. That client takes that secret that it's worked out with that random number, and it encrypts it using the public key that was sent across in the certificate from the server. And by encrypting it with that public key, only the server is able to read that secret. So the client sends that secret back to the server, and the server then has the same secret as the client. And this is important because this asymmetric encryption we've been doing at this stage using these public and private keys, it's quite inefficient, it's quite slow. But now both client and server share a secret together, we can use more conventional symmetric encryption for encrypting our traffic, which relies on having this shared secret. And we switch to a different cipher, and traffic can start flowing using that. Okay. So this is a Cipher Suite. This is what it looks like when it's written down. And kind of here we have all the different parts of what's used inside TLS. So I mentioned this establishing a shared secret using public and private keys. That's done by the key exchange cipher, this one at the front. Here we're using one called ECDHE. And then I mentioned once we've got that shared secret, we can then use a different algorithm to start sending data backwards and forwards encrypted using that shared secret. That's the block cipher, and as the name suggests, that's capable of encrypting a particular block of data, maybe 256 kilobytes, for example. That's not very useful on its own. We need to be able to encrypt much larger amounts of data than that, and in order to do that, we need this next bit, which is the block cipher mode, which is the way blocks of encrypted data are combined together to make one long stream of encrypted data. There's a couple of other bits here as well. I mentioned in the server certificate there's a signature that we can check to ensure the server is who it says it is. That's done by the key authentication algorithm, and I'll come to a little bit more in a second how that all works and how we establish that trust. And the final entry is this hashing algorithm. That's used a few different ways in TLS, but typically that's used to produce like a digest of the data being sent, which can be signed, so that we can check the integrity of the data. So that's providing our ability to know if the data has been tampered with. So within all those different parts of TLS, we can kind of achieve all those things that we said we wanted to do at the start. So This is the list of Cipher Suites that the API security group has selected. There are potentially hundreds that you could choose from, many of them insecure. I'm not going to go into too much detail about the process of doing this, other than to say that we looked a lot at what browser manufacturers and server vendors are using. We looked a lot at vulnerability reports around different algorithms. But if you want to read a bit more on that, I've written a white paper about that selection process that details a lot more of this and explains a lot more of the theory, and I'll link to that at the end. Just to tick off a quick pet hate of mine, you may have heard this technology called SSL. It's not, we don't use SSL anymore. SSL was the protocol that was used for doing this kind of work before TLS. It went through 3 versions, and they're now all considered insecure. We mustn't use them. And in fact, TLS itself has been through a couple of versions already, TLS 1.0, 1.1. They're now also considered insecure. We shouldn't be using those either. So TLS 1.2 is the current best practice. And that's what you'll be using almost all the time to browse the internet. I say TLS 1.2 is the current version. TLS 1.3 a couple of weeks ago received its RFC number, so it is now out there. I haven't been served a web page with it yet myself, and I have been checking, but it's going to be coming through pretty soon, and I'm kind of hoping we'll be seeing it in a few implementations coming soon. The good news about TLS 1.3, it's got a lot of benefits. That handshake I showed on the screen earlier, it looks quite long. It is. TLS 1.3 shortens it, and that is one of the reasons TLS 1.3 is a bit faster. But also, TLS 1.3 only supports secure Cipher Suites, and it supports far fewer than TLS 1.2, which is great news because I don't need to write another white paper on all the Cipher Suites for TLS 1.3. So I mentioned earlier that we can use this certificate that comes from the server to check the identity of the server. But how does that work? How do we actually know that that's something that we can trust? So these certificates, they're issued by a third-party organization on the internet. They're organizations called certificate authorities. And these certificate authorities will sign these certificates to say that the person they're issuing them to owns the domain that the certificate contains within it, and they sign it using a private key that's held extremely securely by the certificate authority. And in order to check those certificates, we can use the public key of the certificate authority in order to validate that key. So as long as we hold the public key of the certificate authority, and we know we trust the certificate authority to only issue certificates to people who own the domains we're visiting, then we can check the certificate the server presents us and know that everything's good. So the whole setup looks a bit like this. So you have the root CA private key, it signs a server certificate, and that's passed down to the client when it accesses the page. But there's a whole other side to this, in that we need the public key of the certificate authority, and when we're on the internet, that process, that reaches us either because our operating system vendor runs a scheme where they accredit certain certificate authorities to be able to do this, or our browser vendor does it for us. And therefore, these certificate authorities are held to extremely high standards and very tightly regulated. But this is something that we're potentially going to have to do for our own broadcast plants in the future, right? We're going to need to be able to have certificates on our cameras, on our vision mixers, whatever else. So to kind of show that this is something that we can do, that this is within our reach. At the last AMA interop, I actually set myself up a certificate authority to issue certificates for the interop. So I had a root CA here, that my sort of super secret key. That produced an intermediate CA because you usually don't use that for signing, you kind of have an intermediate. And then I produced myself a server certificate which I installed on my server that was serving ISO 4 and ISO 5 at the interop. Equally, I took my root CA certificate out and put it into the browser and then hit the ISO 4 endpoint on that server. And this was the result. So you can see ISO 4 running in the background, there's all the JSON that goes with it. And I've secured my BBC2 machine with a certificate issued by the AMWA CA, which is what I called the CA when I set it up. So this isn't sort of a vastly complex thing to do, and there's lots of tools and solutions out there for doing it. And there's lots of protocols available for distributing both the certificates onto the servers and also for getting the public keys of the CA into our browsers and into our client devices. There's a lot more detail in there as to how we can do that and how we can do that in an interoperable way. So I've produced a second white paper that, again, details a lot more of this, and also expect to hear more out of the API security group as we move forward through this work. So that's about it from me. That's the link to the first white paper I mentioned around the Cipher Suites. The second one is white paper 338. Unfortunately, it wasn't published in time for the deadline for these slides to come through, but I'm sure you can imagine how you can change that to be 338 and get the second white paper as well. So thank you very much for your attention, and that's it from me.